Hello, everybody. My name is Bridget Good. I am a community emergency response team volunteer for the city of Salem here in Oregon. I've listed my contact information here. Please feel free to reach out to me at any time with questions. I am going to turn off my camera for this presentation. I don't really feel like the box needs to be there. So let me do that and then we will get started. All right. So what is today about? Today is about answering two very basic questions. The first one is, what is the likelihood that a Cascadia Subduction Zone earthquake will happen in the next 50 years? And the second question is, how frequently do these earthquakes occur? How often have they occurred in the past? So those answers may not be what you expect. For those asking, what are the chances that this earthquake happens? They are likely to find this answer: a 37% chance that it will happen in the next 50 years. In some cases, the 37% chance is described as a roughly 1 in 3 chance, but in both variations, the answer is actually fairly pervasive. It can be found in publications from various universities and state agencies, like those shown here. And from those sources, the probability is further circulated to the public through news organizations, including the infamous New Yorker article that made headlines of its own. And from there, it moves at the community level. So 37% in 50 years. Many read this, flip it, and say, well, that's like saying there's a 63% chance that it won't happen. And when they say that, they're really not all that vested in jumping into preparedness action. 50 years is a long time frame for us to plan for as it is, and 63% chance it won't happen doesn't really feel all that imminent. It comes down to risk perception. This is someone's subjective judgment about the likelihood of an event. And that underlying 63% chance, it sends a pretty loud message. This matters because I believe that we choose to prepare or not for this Cascadia Subduction Zone event based on that perceived risk. So when I kept seeing this over and over again, I started wondering, where does the quote come from? Some digging, and we find that the perception originates from this USGS paper. It's 184 pages long. Within it, data is provided on the process of obtaining soil samples offshore of the Pacific Northwest, identifying past earthquakes that have happened up and down our coast range, and then dating the samples to gain estimated ages of the earthquakes. And from all that, the probabilities are provided. So just real quick, though, it's worth mentioning that this paper was just one of over 18,000 publications, research publications in geoatmospheric and oceanic sciences that came out from the US that year, 2012. So when we think about all the papers published from other countries around the world that year, and in all those years before and since, finding a single probability in a 184-page publication that is just one of thousands every year it really is a bit like finding that needle in a haystack. Yet we put a lot of stock into the risk probability. So it's really good to know where it comes from. So let's say, just for a second, let's think about this research paper like a play that's occurring on a really nice theater stage. Each fact is like a different prop or a setting or a performer. And a theater lighting technician has up until now focused the brightest light on this single statistic from page 2, shown here in purple. It says time-dependent probabilities are similar for northern margin events at 7 to 12% and 37 to 42% in 50 years for the southern margin. The southern experiences more ruptures than the north, which is why those differ. So 37%, that's where the lighting technician has focused. But single facts don't always tell the whole story, and they're really not meant to. That bright light, after all, is just one spot for our eyes to focus, right? The story is so much bigger. During a PBS interview in July of 2023, historian and executive director of the American Historical Association, referring to a completely different topic altogether, said the following: "We do have to help citizens understand that facts are not very useful unless we know how to ask the right questions about them." When it comes to Cascadia timing, this quote rings pretty true for me, because when I started asking these questions and researching this topic 5 years ago, I didn't expect to find what I found. I really didn't expect what I found to so completely alter my risk perception of the Cascadia Subduction Zone timing. It started with understanding the number a little bit better. So these researchers at the top here, John Vidal, Aaron Worth Moriarty, the late Professor Bob Yates, and Professor Chris Goldfinger helped me learn that the 37% chance comes from a log normal equation like the one shown here. The original log normal equation for this was actually created in an Excel worksheet by Professor Seth Stein at Northwestern University. He was using it for risk relating to the New Madrid zone, but the worksheet was later shared and adapted to CSZ data by Professor Goldfinger and his team. So I was really happy to know where it came from. I've got the paper, I've got the equation, but I really wanted to start playing with the numbers. Luckily, Professor Goldfinger was very generous with his time and with his work, and he was willing to send me his spreadsheet. He answered my numerous questions, and he helped me better understand this data. The Excel sheet is very easy to use. You input the red fields at the top. That middle section in black does its magic, and it spits out the blue at the bottom. For the red, we know that the last earthquake was in 1700. Professor Goldfinger provided the mean and standard deviation shown here. So really, we just need to change the start and the end year to see how the probabilities change over time. With a start year of 2023 and an end year of 2073, so we can keep with that 50-year outlook, we can see that here at the bottom, the log normal formula is 36.92, and it rounds up to that 37%. But again, I put a start year of 2023, which is our current year, and it's giving us a 37% chance, which is the same chance that was in the 2012 paper. Well, that was 11 years ago, so more questions came when I learned this. I started wondering, what was the risk 50 years ago? My assumption was that it would have been quite a bit lower because less pressure would have accumulated on the fault, right? I was half right. It was lower, but not quite a bit. It was barely lower. In fact, it still rounded up to 37% chance, which made me wonder, well, what would the risk look like 50 years from now? I assumed it would be just slightly higher now, but this time I was wrong, like all the way wrong. Start and end years of 2073 to 2023 has a probability that's not only lower than the current risk, it's lower than the risk would have been 50 years ago. And my brain just kind of said, what? It comes down to the shape of that curve. At some point, the risk peaks like the edge of this cliff here, and then it starts to come back down. So my next question that I had to ask was when? It turns out if we enter 50-year time frames and we evaluate those time frames into that same spreadsheet at 5 decimal points out, The probability model used in the 2012 research paper shows that our risk of a Cascadia Subduction Zone earthquake, this is important, guys. The risk was the highest it'll ever be according to this formula in 2017. And that risk has been going down ever since. Now, of course, that's not the case, right? Pressure on the fault continues to build. Now, the shape of the curve is only one of three issues with using this log normal formula model. It also cannot account for possible earthquake clustering on the fault. That's a topic for another day, probably provided by someone other than me. And then the third issue with this model is that it's based on 46 earthquakes. So again, here are the mean and standard deviation provided by the OSU team. And to the right, the math showing that 46 earthquakes are used to obtain the mean of one earthquake every 223 years. Now, reminder, the Pacific Northwest has already gone 323 years without an event. So 4 of these 46 earthquakes are assigned to what's known as segment E, shown here in the border. The image was presented that you see here in 2016. It's a follow-up paper to the 2012 publication. Now, those 4 earthquakes are the smallest of the record, and their status as being considered part of the Cascadia record is currently being reconsidered. Professor Goldfinger explains that they are small enough that it's actually hard to tell if they are in fact the result of a Cascadia rupture. They could be a northern San Andreas fault rupture or something from the Gorda Plate or possibly another source. So we have 42 official earthquakes in the last 10,000 years on the record, and changing from 46 to 42 on that log normal formula would, it would change the mean, the standard deviation, and the answer. So despite these 3 drawbacks to this statistic, it remains the top quoted risk out there. But ultimately, I no longer use this probability when talking about the likelihood of an event. And, thankfully, I'm not alone. Researchers are, of course, aware of the drawbacks. They've been working toward a model that can better represent the behavior of the fault over time. In fact, a team of researchers at Northwestern University has developed the long-term fault memory model, and they've applied the model to data from the New Madrid fault, New Madrid zone. Work is currently underway to apply that same model to Cascadia data. So for now, we wait. But back to our analogy of this play. Let's say we want to keep the same performance, the same actors, lines, setting. In other words, for today, we're going to keep looking at the same research publication, same data. We're even going to stay on the same page. But we're going to ask the lighting technician to move his spotlight 1 sentence down. Okay. Here's the new sentence that we've moved the lighting to on center stage. By 2060, we will have surpassed 85% of all reoccurrence intervals. Huh? Guys, that seems like a pretty high percentage. How have we already passed 85%? I really wanted to see what those intervals looked like. For that, I needed the estimated ages of the past Cascadia megathrust earthquakes. Luckily, they're listed on page 97 of the same paper. From this list, which is just a screen snip on page 10, we will take away event T10, which is, again, it's one of those smaller earthquakes from segment E that I talked about earlier. It remains undated, and its status as part of the Cascadia record is in question. So we are going to pull that out. This leaves us with 41 major earthquakes in the most recent 10,000 years of history. However, we need to add one more. The publication discusses and adds event T19 to this data as well. And so we are going to add that here. And if we plug these dates into Excel, we can actually calculate then pretty easily how many years were between each earthquake, also known as the intervals. So this is where things get kind of fun. We can take those intervals and ask Excel to display them in a bar graph. Each bar graph here represents the number of years in a single interval. Those intervals are listed in chronological order, with the oldest, the interval that fell between event T19 and T18, on the left. The newest interval is shown here on the right. Now the horizontal black line is running at 360 years. That is the amount of time that will have passed between the last major Cascadia earthquake in 1700 and the year 2060. So that's the year mentioned in the USGS paper. If an earthquake doesn't occur by then, intervals over 360 years are shown in red, while shorter ones are shown in gray. We've got 41 intervals. Only 6 stretch above that black line, and they're clumped together. More about that in a minute, but here's the math. Out of 41 intervals, 85% of the time, the intervals didn't stretch as long as we've gone without an earthquake now. So we have currently, by the year 2060, passed 85% of intervals. Now, that's kind of a ways out, right? It's not 2060 yet. What does the current data look like? That's what we really want to know, right? How does it compare to right now? So again, the Pacific Northwest has currently gone 323 years without a major earthquake. This bar graph drops the horizontal line down to 323 years. And this, it's meant to help us easily identify past intervals that lasted longer than our current quiescence. As before, intervals longer or larger than 323 years are shown in red. And there still aren't many. If we look at the math, even as of today, 80% of the time the fault has not had to wait 323 years for the strain to break it. And notice when those longest intervals occurred, shown here with the yellow border. Those longest intervals are grouped in the oldest 4,000 years of history, whereas intervals 1 through 28 include the most current 6,000 years. So let's zoom in on the most recent 6,000 years of history. Oh boy. Only 2 intervals, shown here in red, have actually been longer than that black line. This is as of today. And if you take nothing away from this presentation, I hope this image stays with you, because these 2 lines don't stretch very far above the amount of time we've currently gone without an earthquake. One is only 7 years away, and the other one, the longest interval that has happened in the most recent 6 millennia, is only 21 years from now. So it's really hard to be talking about 50-year outcomes when I see this. So if we take those 28 intervals minus the 2 red that are longer, we get 26. We calculate this out, and 93% of the time, the fault has not had to wait 323 years for the strain to break it during these last 6 millennia. That's as of today, guys. This is not a 50-year outlook. That's as of today. We've already passed 93% of reoccurrence intervals. Now, let's look at the 6,000-year chunk of data and project it out 37 years to that 2060 year that was discussed in the USGS paper. If we do this, not a single interval would stretch that high. In fact, the Pacific Northwest, it only has to go 22 years to pass the longest interval in the most recent 6,000 years. 22 years. If only the most recent 6 millennia are considered, guys, we really only have 22 years until we pass the longest interval on record. When I learned about those interval lengths, my mind was blown. My risk perception completely changed. I completely understand, though, not everybody loves hearing about probability numbers, so we're going to look at that second question we talked about at the beginning here. Let's say rather than wondering about the probability, you're a community member who just wants to know how often do these earthquakes happen, right? So you decide to go in search of the answer through, of course, reputable resources. If we think about 2 earthquakes being the sides of this canyon and the space between is an interval, what we are essentially asking is, how wide is the canyon on average? Regarding the CSE megathrust earthquakes, a community wanting to know the answer might find answers like these. Cascadia earthquakes happen every 500 to 600 years, according to the Government of Canada and the Cascadia Region Earthquake Work Group. While the State of Oregon Emergency Operations Plan lists 300 to 600 years as the normal reoccurrence. We could look at the Pacific Northwest Seismic Network and see them occurring every 400 to 600 years. And the USGS, the City of Seattle, and Berkeley Seismology Lab list every 300 to 500 years. You can see how it would be really confusing, right? Because we trust all these organizations. These are reputable organizations. So who has the right answer and why do the answers differ? More importantly for today's conversation, though, what risk perception do these answers provide, right? So let's think about that for a second. We know when the last earthquake occurred, January 26th, 1700. We know how long it's been since our last one. It's been 323 years. So if we only had the answers shown here on this page, that the earthquakes happen roughly every 300 to 600 years, if we take the lowest and highest here, you're going to get a map that looks a little bit like this. You are here, right? And the risk doesn't really feel all that urgent. It's like, oh, okay, we probably have a few hundred years before it happens. Well, that's not the case, though. We look here again. Does saying that intervals happen every 300 to 600 years feel like the best representation? I mean, it's not wrong. We have intervals that have gone almost to 600 years, but is that really the best representation? Well, it's a little hard to see it in this form. So we are going to look at it rather than intervals chronologically as they are shown here. We're going to stack them, smallest to biggest. So here we have 41 boxes, each representing one interval. The number inside each box is the number of years that passed between 2 adjacent megathrust earthquakes. The numbers are the same as in the previous bar chart, coming from the years provided in that 2012 USGS paper. And if you were to look at this and you were to tell someone how often these earthquakes occur on average, would you pick every 300 to 600 years as the best represented time frame? Or maybe how about this? It bears repeating that if the scientists are correct on the timing of these past earthquakes, the Pacific Northwest has not gone longer than 344 years without an event in over 6 millennia. And if we look even at the full 10,000 year history as is shown in these boxes, I really believe it's more accurate to say that we are here. So how we talk about this risk matters. It impacts our risk perception, which ultimately guides our motivation. So we're down to the last 2 slides and a couple of final thoughts to leave you with. This is a screen snip from a 2018 FEMA prep talk by Amanda Ripley. It's titled The Unthinkable, Lessons from Survivors. I highly recommend watching it. Amanda says, it is the regular people, your friends and family and coworkers and hotel workers who will be there for you in a disaster. So our best chance is to trust them with more information sooner, more transparency than we are comfortable with, and then we will know we are doing it right. So here, written in orange, are the scientists involved in gathering the Earth cores, analyzing the data, and publishing that 2012 and follow-up 2016 papers cited at the bottom. They have worked really hard to provide this information to us, information that goes beyond a single fact, that provides a backstory worth knowing. Again, my name is not on this list. I am not on the stage for this play. But what I hope to have done well today is to serve as that lighting technician, adjusting the spotlight on a new direction, one where we do not normally focus. So thank you for coming today. If you have any questions, please feel free to reach out.